Hello everyone, it's June 24th, another morning session. Um, ready, feeling much better um, from that second COVID shot, so nothing more to complain. All right, today's question is called out of boundary paths. I see a soccer ball. There is a m times n grid with a ball. The ball is initially at the position, okay? You are allowed to move the ball to one of the four adjacent cells in the grid, possibly out of the grid, crossing the grid boundary. You can apply a most max move on the ball. Given the five integers, mn, max move, start row, start column, return the number of paths to move the ball out of the grid boundary. Since the answer can be very large, return the modular. Number of paths to get it out of the boundary. So m, n, 2 by 2. Max move is 2 moves. Start row is 0. Start column is 0. So we have, okay, 1 move, 2 moves. If it were in here, oh, hold up. 1 move, 2 move, 3 moves. 1, 2, 3. 1, 2, 3. 1, 2. Oh my. My, oh my. Okay, feels dynamic programming to me because let's say we find all the positions that one move can get out of bound. In this case, which is these four positions. So these four positions is one move, and we see if the ball can end up in this position, and we can. So that's one, right? And for two moves, basically we say, given the ball at the current position, can we do one move to make it end up in one of the positions that one move can get out? And because these four positions are the one move eligible position, and we say this one can get to two of them, right? So it can get here. Oh, and actually it's slightly more complicated because one move, these are one move, but one move actually there are two moves. So we can here, that's two, and we'll go here, that's also two, right? So if we say three moves, right? Three moves, that means we need to find the positions on the grid that two moves, right? That when you end at that place, two moves can get out. So for example, this is a place where two moves can get you out, right? The two moves can get you out, and actually there are four ways that two moves can get you out. So we just have to search, go through the entire grid. It's 50 by 50 at most, or 2500 at most. And the moves is 50 moves, so we probably times 50 again. That's the total amount. So we identify the position for one move, right? And then we need to identify the positions for two moves. Okay, let me think about it again. So wait, identify the positions for one move, right? And then in those positions, we are going to record the number of moves, not the number of ways, right? The number of ways that one move can get us out of bound. I mean, one move basically is just on the top, right? On the edge, right? On the edge. And then we say we're gonna go through the entire thing again and see if at those positions we can do one move, do we end up in the previous one? in one move can we end up in the one move eligible places? If we can, then that's a 2 move, right? So we record that position as a 2 move, and then we find the total number. So we go through everything again, right? And then we go 3 moves, right? 3 moves. So we go to the 2 moves, right? We go to the 2 moves, and go to the 2 moves, and we need to say, if we do 1 move, can we end up at the 2 move stage? If we can, then we record, right? And we go all the way until we hit the number of moves, right? Until we hit the number of moves, until we hit the number of moves, and then we look for this value. So they're gonna be a lot of 2D arrays. So I'm thinking, is it possible to use only one 2D array to handle everything? It is. No, I don't think so. I think we need 2. Yeah, we can use 2 because we only use the one that's previous. Okay, so yeah, let's try it. I have a general idea of how this one can be resolved. Do 24. That's good. Okay, copy and paste. All right, so what we need is, so M and N is the grid, total number of grid, right? So we're gonna say pre-grid is going to be so the 1 move is the base condition. So can we make that? Well, not really. But we can code it. Yeah, we can code the base. Okay, we call the base condition inside. We say 1 move, right? Which means this one will give us 0, right? Everything will give us 0. So hold on, let me think. That's one way plus whatever, so that's 1 plus 1. Yes, I think it's fine. So we're going to just say 0 times m is the number of rows, I think. I believe, yeah, n is a row. So this is going to be n for this range m, right? That's pre. And for move in range 1 to max move. Well, actually, it doesn't matter because we don't really care, because every single time we just need to be +1 to see. Yeah, we just do 1 move. So I don't think this is necessary. Let's just do this, right? In range max move. Every time we're gonna produce a new one, right? Call it current. Current is the same thing, and we say for I in range m, for j in range n. So what do we do is, if we can reach, I do think we have to do it separately. So let's have move as well. Right? We just say if move is 1, the first move, then we say what? For dij, I think I should put it here. For dij in, that's the direction. So we have up, -1, 0, go to the right, 0, 1, go down, 1, 0, and go left, 0, -1, right? We do that and say ni nj equals I plus dij plus dj, right? And then we say if that equals 1, so it's the initial move, then we say if ni is smaller than 0, or ni is larger than m, or nj is smaller than 0, or nj is smaller than n. That's out of bound. That means it's out of bound. Then we say current, right? Current ij plus equal 1. And we'll go through all of them, right? Otherwise, else, so move is not the initial move, then we have to check on the pre. So we say, and then we have to make sure. So we're going to say if 0 smaller or equal to ni, smaller to m, and 0 smaller or equal to nj, smaller to n, and pre ninj, right? Ninj is n pre ninj is not 0, right? It's not 0. That means we can get there. Then what we're going to do is say current ij equals current ij plus equal, right? Plus equals pre ninj, the number of ways for the pre, right? The number of ways that the pre can do, and then and that's just plus equal to pre then, right? Because in this case, I say this one, I add the 2, and add a 2, so that's 2 plus 2, 4, 5, 6. So I think it's just add that. Which means if I can get them to 1, then we can combine, but I cannot. It has to be considered differently. Which means if I do it on the outside, then we can make it slightly easier. Okay, let's just do it outside. I don't really like it. Let's do it on the outside. So we'll just say for j in range n, we're going to say pre 0 first row j equal to 1, and pre -1 last row j equal to 1, right? And then for I in range m, then we'll do first column pre I, first column 0 plus equal to 1, plus equal to 1, plus equal to 1. Then we can handle the two case as well, right? On the 4 corners we can do that. So there's the last column plus equal 1. That's it. And then from here we can go that we don't need this anymore. We don't need a move anymore. So we can just say range, max move -1, because we don't handle 1. And then we say current, do blah and blah, do this, and we don't have to handle this case. All we need to handle is this case. Right? Once we're done all that, we just need to return current. Oh, we have to also replace. So once we finish updating current, we're going to say pre equals current, and eventually it's going to be pre start row, start column, and we're going to mod 1, 2, 3, 4, 5, 6, 7, 8, 9, 7. Okay, let's test this. First test case, 2, 2, 2, 0, 0, 6. Second test case, 1, 3, 3, 0, 1, 12. Okay, so it's a lot. I have M, N, max move, start row, and start column. Then this one will change to find paths, MN max move, start row, start column. Try it. Ay, not correct. Not correct. Okay, it's fine. We just need to, I think this is the problem, right? Actually, we have a problem with the first one. It's fine. The DP is not 100% correct. After the first one, we can print out. Let's print out. Print. Yeah, that's for row in pre. Print pre. What is this? No, print pre. Print row. Huh. That is not what I had expected. How? Oh, well. Hold on. Yeah. That is weird. I'd expect the 2, 2, 2, 2. I think something wrong here. Okay. Oh. Oh, no, that's fine. For I. This should be I. That's a -1. Column, right? Column. That's the first column. That's the last column. There we go. Yeah, I know something was wrong. But it's still not correct, which is fine. Which is fine, because we're going to take a look. Let's just do it here after each round. So eventually we get a 4. Oh, but 4 is the number of steps, the number of ways that at a max move equals 2 will get. So we need to have a result. We need to accumulate, right? Which means after this, right, after this, pre equals current, right, going back up, what we're going to do is res plus equal to this thing. And then when we return res, that is still not correct. Because res needs to equal to this. Yeah, because as a start, we just didn't count this. And now every time current after done, let's actually call it current and do it before this. And we update res. Now this one will pass. Both pass. Okay. Now we can take a look here, and let's run some heavy loads, right? Let's say 50, 50, 50, 50, max move 50. So that's the maximum, and doesn't matter. Let's say 12 and 13. All right. Let's see how fast we can get this one done. Finished. Oh, I think we got it. Edge case. Zero move. Zero move. Should be zero, right? Yep, I think we're good. Submit. Pending. Judging. Hey, we got wrong answer. How? How did we get wrong answer? Huh? How did we get wrong answer? Want to see? I really want to see. But the wrong answer. And what is a situation we didn't consider? No, I don't want to see. I want to try. We're still early. Only 20 minutes in, so I want to try to find out the error case that we have. So now this is right. Let's do some wild things like this. Basically, just throw some weird stuff and see if we got it. Okay. One move. One move. That should be zero. Fail. What could be the edge case? One row or one column. Expect start column to have values from 0 to 1 only. Yeah, because I don't have 50 rows. Yeah, let's go like this. Let's go one row, 50 columns, and then one move. We start at 3, 0, right? Start row. Oh, row has to be 0. This can be 3. I'm just trying like very weird test cases, see if, okay. So how about I say 50 moves? Lots of moves, just on a single strip. Ha! What is the problem, man? I honestly have no idea. But we do have a wrong answer. I don't know. What could be? 50 columns, 50 rows, 3 moves. I don't know. Putting random values. Do I have a? Oh my god. All right, I need to see. I want to see the error case. What is this? Come on. Oh, here. It's a medium question, as expected. I don't want to see the result. I just want to see my wrong answer. I pass 91 on 94. Okay, so, 0. 91 of 94 test cases. So we're almost there. Okay. What is this? 3. Let's try it. So this one, run. What case I have not considered? Was that 3 rows, 8 columns, 0 moves. Ah, I think I know. Dang it. I know why. I know why. I know why. Yep, I know why. So, because I assume that there will always be 1, but it's not. If it's possible, we can move this part inside. But if we move this part inside, that's just... Oh, we do a check. Alright, now we do a check. Alright, let's just do a check. If not max move, just return 0. Simple check saves the day. Because I like how we handle the 1 case, like the base case. If we don't handle it this way, and we need to check the pre, right? The pre is all 0. And none of them will, and we won't be able to, so we have to have another condition here. Yeah, I like this one. I like how it is. So I can put, this is a base case, right? So this is a base case for the first move, right? For 1 move, not the first move. For 1 move. And then everything else follows through. I just forgot to check the 0 move. And yeah, it was on me. Yeah, this one shall pass. Yep, there we go. So, failed a little bit. Alright, not very difficult. A typical DP problem. We record the number of ways to move out of bound for each consecutive moves. For instance, with move 1, we have all the edges eligible to move out of bound. We record the number of ways each eligible cell can move out of bound. Basically, everyone on the edge has 1 way to move out of bound with max out of bound, except for the 4 corners, which have 2 ways. Then we consider the second move. We go through each cell and see if a cell's next move can end up at a cell, that is eligible for a 1 move out of bound. For 1 move out of bound. If a cell can reach, if it's possible, right? If it's possible, we increment the number of ways for the 2 move eligible cell with the value in with the number of ways in the one move eligible cell. We continue this operation until reaching max move. At each round, we increment the result by adding the values, the number of ways at location start row, start column for the current move. The tricky part that got to me was that I forgot to consider the zero move situation, but it was resolved by simply setting up a check at the very beginning for max move equals 0. So the runtime is max move. Let's call it K. KMN. I said 4KMN, but that's fine. Where K equals max move, M is the number of rows in the grid, and N the number of columns. Yeah, I think this is a very typical solution. Nothing special. Oh, why am I so slow? That means there is a better way. We are at 364 milliseconds. Only 18% ranking. Alright, interesting. Let's see. This is my fastest. DFS. Well, it's very short. Let me see how fast you go with the longest thing. We don't need this one anymore. Let's try this run code. Alright, it's at 36 milliseconds. We go 50, alright, 50, 50. Let's see how fast it can go. 72. I guess that's not a good way to test, right? I mean, even if the DFS should be exactly the same as this one. Oh, wait, no. This is slower. Oh, wow. DFS is faster. Much, much faster. Twice. More than twice faster. I think we're wasting. Yeah, I think this is what it is. We're wasting. True. We can reduce, because the only cell that we care about is this, right? The start row and the start column. If we only care about the start row and the start column, all we care about is like a current step, right? The start row can only move one, so it can move up, left, down, and right. And that's all it can do. right? So it only cares about how much that they can get. But it does involve the rest, or does it not? Say 50 moves. Oh, okay. Let's see why the DFS is faster. Brute force. Find a path. If this or this, return 1. If n is 0, return 0. Otherwise, it will find path. And then we go up, number of paths. Oh yeah, go to the end. Recursion memorization, dynamic programming, NMM, yeah. Isn't this what I'm doing? But why is it slow? This is Java. But I think this is what I'm doing, right? DP. We have a temp. Yeah, that's the same. DP xy equals 1. Count is 0. We get a new one. We have these two. If j is equal to, then count equals this. That's the edge. Right, that's the edge. Count plus dp this. Count plus dp this. What is count? I think count is the total we return. So if m is on the edge, right? So go through everything, go through the moves. So if I am on the edge, what is j equals m minus 1? Oh, that's I. It's the last row. Then so if I am at the last row, then I just add myself. And dpij I feel like it's slightly different from what I was doing. First move. Right? If it's first move, then count plus dpi, that'll all be 0. Temp ij, if I larger than 0, then equals this, otherwise 0. I think it's a slightly different way of thinking. But I do have one suspicion. What if I have the count doing this every single time? Maybe it'll be faster. So instead of doing this at the end, what if I do this plus how should I say it? This one equals rest plus this, and let's do this and see how it goes. Run. No, that is not a problem. Huh? Then I don't understand. Feel like the same to me. Yeah, the same runtime. But why the? If we can reach some position in x moves, we can reach all its adjacent positions in x plus 1 moves. Use a DP array to store the number of ways in which a particular position can be reached. Number of ways the position corresponding to the indices can be reached. Number of ways the position corresponding to the indices can be. Oh, it's different. It's recording the number of ways that the position corresponding to this can be reached. That's why when it gets to this, right, we reach the end, then we increment, right? Reach the end, then we increment. And my way is different. I'm recording the number of ways starting at this position that you can go outside. So it's the same concept. But I still don't understand why that is faster. And it's also simpler if you think about it. Right? It's also simpler. Oh, this is just a simple memo. We remember the states, n and n plus 1. So that's also that's the same. Hold on, let's see. Educational matrix exponentiation. What's that? Complexity n to the third times log n. Okay, that's not the one. I will just cache it. Oh, I think it's the same as the top. Are you saying using cache is faster? If this, we reach boundary, return 1, and find one more path. If it's 0, finally we try to make 4 steps to all directions and return sum of all number of options. Third line, only if n larger than 1. Call function with first argument, numbers move to negative. Yeah. Cache, return 1. If n is 0, return 0. And then for each position, we're gonna go n minus 1. And then this one will go until we find the path that will return 1. Yeah, DFS just keep going. And then we're saying that if we have visited a cell before, then we don't have to visit again. And the state is total number of moves so far and the current position. If I visited again already, then we don't have to visit again. And this, they will try 4 different positions. Yeah, so for each cell, we're asking to know at step n, right? We need to know the step n minus 1, my 4 things. So we go for all these, and yeah, it's the same. But why would mine be so slow? Is this one also fast? I don't know, man. I don't need this one anymore. I have no clue, like whatsoever. Why? Oh shit! I have to. Let me do it. 50, 50, 50. Run code. Come on. Yeah, it is damn fast. What the heck? Why are you so fast? And this one is so slow. Max move is not defined. Oh, it changed everything. I don't understand why. I mean, the only explanation I can think. Yeah, look at the runtime. It's exactly the same thing. So I think it's because of um, how should I put it? It's because of the number of loops we're using. I have read that loops are very slow in Python, very slow. So now we have tons of loops. We have one loop here, one loop, another loop, and we also had to do all this loop, right? So we have lots of loops, and it's actually here too. We have a lot of loops. We have one level, two level, three level, and I mean the last level. The last level be done in a loop comprehension. So we can do as a comprehension the last one, which maybe we should do it. Maybe it'll make it faster. Let's try it. Maybe we will make it faster, but how do we do it as a comprehension? We definitely need to define something else, right? We need to define directions. So this is directions, right? This is directions, and probably right directions, and then we say, actually it's fine in dirs, and oh, we're not returning anything, so I don't think this is possible. And dirs, and even this and dirs, get a thing out. Yeah, we're not returning anything. I don't know. This is like micro optimization. Will this mean anything? No, it doesn't mean anything. So all I can say is, I mean, oh, another thing is we have to set up this every single time. That is costly. I know that is costly. And if you do a recursion without your cache, this part is cached for you, and it's done through Python, which is optimized. So that's the only explanation. That's the only explanation, which I want to try. I mean, it's not really difficult to code. It's very simple to code, but it's good to try. So I'm going to say functools import LU cache, right? So here, basically says it's going to be solution 2, right? And we say def DFS, right? So what do the DFS do? So we need to go to I, J, and number of move, right? I, J, number of move. And this one gonna return an integer. And everything is integer. J is integer, and this one is integer as well. So I'm gonna say if I is smaller than 0, wait. Yeah, if I is smaller than 0, or I is larger equal to m, actually it's not, it's just, okay, say equal m, or j is smaller than 0, or j is larger equal to m. If that happens, then we say return 1, because that's the path we found, right? Otherwise, we're gonna say oh, hold on. We also have to be num move, right? Yeah, it has to be num move equal to 0 as well. If the move is not 0, the num has to be 0. Num move has to be 0. If num move is not 0, then we do not count. So it has to be if num move is 0 and this, right? I'm actually going to put up parentheses as well. Then we return 1. Otherwise, we're just going to call DFS and return sum for di, dj in the directions, di, dj in directions, and we're just going to say DFS I plus di, j plus dj, num move minus 1. Right? So do all this. Once we've done that, I'm going to say return DFS ij would be start row, start column. That's what we start with. And num of moves is max move 2. Oh, and we have to also say if max move, else we'll just return 0. That was the problem. I think it's a max recursion, right? We haven't done it. Yeah, max recursion. Yeah, it's understand because I was just trying to see what's going to happen. Okay, so we have to say at ARU cache. What's the max? I forgot. It's not max move. IO cache. Max size. Max size. Wait, is it max size equals none? Nope. Is not correct. Oh, I know. If num move is 0 and this return 1. If num move is not 0, I know. So if this, which means we go out of bound, and we say return 1 if num move is return 0, else return 1. Still not right. Why? Max recursion depth. We go 4, right? And then every time we go, it's gonna num. Oh, it's not num moves. It's map. Oh yeah, it is num moves. Current moves minus 1. And then we say if there's still moves and then we move out of bound, then we return 0. Else we return 1. Why would this time out? Oh, this. Wait, what did I do wrong? Num move. I is smaller than 0, or I is larger equal to n, or j is smaller than 0, or j larger equal to n. That means I have gone out of bound. If I've gone out of bound, then we're going to say if there's still move left, right, then we go 0. If there is still move left, that means we reach it with not using max move, then we return 0. And if there's no move left, move is 0, then we return 1, right? And then for each one of them, we're gonna go for 4 directions, right? 4 directions, and start with max move, and we start from star row, star column. Wait, I don't understand. I honestly do not understand why this one would not be right. I'm going to comment out these two. Okay, so let's see what happened. Right, let's print out ij and num move. The num move keeps. Oh, I think it's because if. Why would the num move be negative? Oh, it will be negative if I go to another position. Ah, I have to check for num move. Hold up, hold up. Oh yeah, I have to check for num move. If num move is equal to 0, okay, it should be if num, yeah, that's if num move equal to 0, right? And we're gonna return 0, return 1 if this. Yes, I think I got it reversed. Else 0. So we do not keep going if num. Okay, now we have a different problem. Num move equals to 0. If num move is 0 and I am at out of bound, then we return. Hold a sec. Why? Result 10. Something gets double counted. It's not obvious, right? Print ij in the move. Let's see. Now move 0. Oh, look at this. It's -2. Ah, I know. This has to be, I think we have to, or I equals m, j equals -1. It can only be 1 out. I equals. Ah, we reduced some, but still that's not right. Ah, because the other one, we have to restrict. Hold on, let me think. So the I, like we need to say like this is not going, right? I is -2. It cannot be. Yeah, it cannot be. So, what's the condition? Let's see. If num move equals 0, right? If it's inbound, because we need it to be just out of bound, which means what we need to check is if it's on the edge. I think it's only one of them can be. But this one will not return, right? This one will be, oh, this is counted. -1, -1. How do I prevent this from counting? If num move is 0, right? So we have no more moves and we need to be out of bound. But there are only so many places so we can be out of bound, right? Which is I equals 0. No. I equals -1. Then J must be from, J must within bound. What are the better ways to do this? Or we can say, if number move is 1, and I am at the edge, then we return 1. And then that could be wrong, because if I am at the 4 corners, we actually should return 2, because from there we have 2 ways to go. It'll be best if we can get outside the bound, but just the outside the bound, there are 4 edges. Yes, exactly, we're counting the 4 edges twice. How did you not count them twice? I mean, I always see this one gets very complicated. Like, if I is out of bound, then J has to be within bound. And if J is out of bound, then I has to be within bound. Right? So what we need to do is, if we say I is out of bound, then we say J within bound, 0 smaller equal to J, smaller to N, and so the J within bound, I out of bound, or I within bound, and J is out of bound, right? That will pass. I think this will pass the rest as well. No, it does not pass the second one. No, I think it's still not right. Result 27. The hell? Why? Four directions, right? From this position, and then we go, and if equal to 0, we do this. If it's smaller than 0, we should return 0 immediately. Then we already said and this or this equal to this. Oh, I think this is wrong. This is M. That's still not right. Change it to M and it's still not right. Let's say I within bound. J could be -1 or J could be N. What is the end position? So, like, num move will become 0, and then we check. Right after we check, we return immediately. Right? So if I do ij num move shall be 0, I can be minus 3, minus 2, minus 1. These fine because they will not, if this or they will not be counted, right? 2, 3, 4, 5, 6, 8, 9. Yeah, it will not be counted. I don't understand. Every position with a current number of moves, right, and have that many foot directions, and we add it together. And if number is 0, but it's not outside a bound, then we return 0. Do I have to put another parentheses just because I have a long one, just in case? No, that's not a reason. I don't know, man. I don't know. I don't understand. Yeah, num move is 0. Hold on. And then this is not necessary. Yeah, I really want to understand this. So let's say S equals this, and we're going to return S. But before doing that, we're going to print ij, num move, and S. Right? And we have 0, 1, 3, give us 27. 0, 1, number move, 3 moves at the position, right? At position is 0, 1. And this say we have 27. Okay, so we start. The start is wrong. Minus 2, 1. How could you have minus 2? How could you have minus 2? I and j has to be in bound. I and j has to be in bound. So what would this happen? ij move, number of moves. So number of moves is 1, right? I is minus 2. Huh? J is 1. So basically from here we go up twice, 2 moves, and we have 1 move left. And we go to the next move, and then that move is 0. And basically it says return 1. Oh, I know, because I moved to here, one of the move will bring me down. Ah, that is the problem. Holy moly. So what we need is to make sure num of move equals 1, and you are on the edge. Ah, you cannot set it outside because it can move on the outside. Okay, so let's try 1. All right, then how do you consider the 4 edges? We say if I equals 0, or I equals m, or j equals 0, or j equals n, that means you're on the 4 edges, right? Then we're going to return but there are situations where you need to return 2. Then we just consider it again. So let's make sure they're in the edge, right? And then we say if it's on the 4 edges, which is if I ij in, man, I don't want to do this. This is stupid. This is literally stupid. And I'm going to do else and return 0, right?
Ow! Ow! Why are you training them to bite?
No. Move is 1. Then we return, right? And I'll say this is stupid. Like 0, 0, 0, column n minus 1, n minus 1, 0, n minus 1, n minus 1. That's going to return 2. Else, return 1. And then at the end, let me say return the sum. I think this one shall be right. But it's just stupid, right? It's just so stupid. What is the way to detect? If I equals m, j equals n, or I smaller than 0, or j smaller than 0, then we return 1. I think we're talking about different things. A path. As long as I reach outside, then that is a path. Because it doesn't matter. I mean, what this requires is, given this, and I want the number of moves I need to get out, right? What this says is, I don't care how many moves, smaller equal to this number of moves. I think the two is slightly different. What I'm saying is, I want to know the answer starting from this move, right? And then I want to know the move of these. But why would these be the same? Because I go through all of them. Because I require the num move equals 1. Right, num move equals 1 and I have to be on the edge. That's one I count. Let's say this says an ij I have to take exactly number of moves. This is exactly 3 moves. And this should be wrong. Why would it still be correct? I don't know. I'm very confused right now. This should not be correct. I don't think this is correct. Because I am testing, I'm running on something very different. What I'm running on is the exact, right? Which means if I do give this crazy test case, this should not be right. Oh, I didn't. Yep, it is not correct. It makes sense that it's not correct because I have restricted. I say it must be, basically this says, what is the number of steps, right? When we exactly need to take 50 in order to get to the end. But the actual question is, what is the number of steps to take smaller or equal to, right? Which means we don't care about number of moves as long as we reaching outside, right? As long as we reach right outside, then we count as 1. And actually, this is not right. I should be m minus 1. If you want to do it this way, it should be m minus 1. This is not right again. Yeah, this should be m minus 1, not m. But I would expect it to be smaller. Why would it be 14 instead of 12? Exactly 1 move. And I'm at these positions, right? And we say if I is in these, I is in these, j is in these, I would say ij is in this, 0, 0, 0 and minus 1, m minus 1, 0, and m minus 1, m minus 1. Then I return 2 because I say in those positions there are 2 ways to go. Otherwise, there's only 1 way to go. And I say if move is 1, I shall return 0. Doesn't make sense, right? It does not make any sense. Why would it be? Why would this be bigger? It should be smaller. Because I'm only counting taking 3 steps, right? I say I take 3 steps. At a 0, 1, I'll take 3 steps. Exactly 3 steps. This should only give me It should only give me 4. The answer for this should only give me 4, because this one, yeah, 1, 2, 3, 4. It should only give me 4. Oh. So this is actually have 3 different ways. Wow. It's very wrong. No, yeah, this is not correct. This is not correct. And we got lucky here that we can consider this one as well, but this is not correct. But why would it be a higher number? I'd expect it to be a small number. To take 3 steps, right? And then we'll have 2 steps. Say exactly 2 steps, and then it will take 1 step. And then in 1 step, I'll check. Oh, I think the exact same thing happened again. It just goes out and come back in. I can do 1, 2, 3. That will count as 1 as well. Therefore, the only way is to check for out of bound. Right? The first time that you reach out of bound, yeah, so if I smaller than 0, or j or I larger equal to m, or j smaller than 0, or j larger equal to n, once this happened, then it means we already go out, so we return 1, right? Else, yeah, if we reach this equal to 0, then we haven't done anything, that's going to return 0. That means we have not reached out of bound, but we have exhausted our number of moves. And then we return this. And in this case, I don't even have to check, because max move will be checked inside. Okay. Yep. This is the recursion. Yeah, I got massively stuck here. The recursive solution. Courtesy of. It shouldn't be, but you know, this happens sometimes. Got stuck because the understanding of the exit condition is confusing. However, as I was trying to write it myself, I got massively blocked by the terminating case. I was checking for num move first, and then checking for num move, first, and then the position of I and j, and then I and j. This is not correct because I and j can be out of bound for multiple moves and eventually end up at the right position that I want. However, yet this is not a correct case. E.g., we want to take 3 moves to get to 0, 0, and we have 0, 0, 2, minus 1, 0, 2, minus 2, 0, and we go to minus 1. 3 steps to go. Then we go to this one. 0, 0, 2, minus 0, minus 2, and then 2, minus 1, 0, right? So 1, 2, 3, 3 steps. So we have achieved going from 0, 0 to minus 1, 0 in 3 moves. This shall count as a move away, right? No, because we went out of bound for multiple moves, which is not allowed. Therefore, the correct terminating case is to check for out of bound first. As long as we go out of bound for the first time, that is a valid way. And after that, we check for num moves. Yeah, that one is embarrassing. Anyway, this one will be right, and that will be it. Oh, and one more thing to say. The speed, right? The speed. One more thing to mention is the speed. This solution has the same complexity as solution 1, but it runs 124 milliseconds, much faster. This is most likely due to ARU cache being optimized, being more optimized than preparing the DP table ourselves. All right, that's it. I've spent like what, almost an hour just to go through this recursion. This simple test, right? Simple test. I thought I can get it very fast, but boy, was I wrong. Anyway, that'll be it for today. I'll see you guys tomorrow. Adios.